Hi everyone. I think people are still sort of settling. I think my voice is fine. It's audible, right? Awesome. Hi everyone. Namaskar. I think my accent is terrible here. um, how's everyone feeling right now? Lethargic? Sleepy? Want to just rest? Okay, I think Shayak gave me this task. He's like, why don't you take it as a challenge to wake people up? So I'm going to try that. I'm not sure if I'm going to be like fully successful, but let me just, attempt that. Thank you so much for the introduction. Great to be back after like more than 2.5 years. And coincidentally, my last in-person session or talk was also in Kolkata with the same, organized by GDG Kolkata. So I'm super happy and super excited to be here again. Um, so yeah, my talk is about building semantic search engines. We're gonna very soon understand what that is all about. But before we delve into that, let me just go to the next slide. I think my introduction has already covered all of this, so I'm gonna skip just one question. Does anybody here use Jupyter, by the way? Oh, wow. I was not expecting that. So that means that you already have interacted with a couple of sort of products and features that I have contributed in building. So that's great. I would love to have feedback. But moving on, all right. So today we're going to cover what's the difference between web search engines and semantic search engines. What is the science behind semantic search engines? What kind of frameworks, or like a generic framework or a architecture that we use for building semantic search engines? And why is it such a hard problem? People often say in the industry as well as in research that search seems to be an unsolved problem. So we're gonna I'm gonna take a jab at it, like why is that so hard? And then what can be done to improve such systems over a period of time? All right. I'm gonna ask, like, is there anyone who hasn't used a search engine? Anybody? I hope not. All right. So search engines are ubiquitous, right? They're a part of our lives. We use them every day. We use them several times, in each day. I think we're kind of dependent on them. I'm going to show you why. So yeah, Google, Yahoo, Baidu, Bing, DuckDuckGo, these are just the most common ones. But apart from this, you do use a lot of search in the other apps as well. Like for example, in WhatsApp, if you're searching for a contact, in your phone book as well, Instagram, everywhere. I don't think that there is, a high-end app which we're using, which everyone's using, which doesn't have search capability. So the question is what are search engines, but I'm gonna maybe tweak it a bit and ask, can any one of you answer what do search engines do? Like, what's the utility? Anybody, can you please?
And when we search according to those data, we get the links we needed.
Right. That is one answer, which is correct. Anybody else would like to take a stab at it? Yes, please, go ahead.
Am I audible? Okay.
Yes.
So basically, in search engines, we index the data in a database, and then we pass a query according to our own, like whatever we are trying to search, and then it actually analyzes what input we are providing to the engine, and then it returns the answer according to it.
Okay, you actually went into the more technical side of search engines. My question, I think you answered it. You actually answered that question, but would anybody else want to maybe just answer it in a very vanilla way? Your answer is actually, you're on point, sir. But what I want to ask is, what does it do? Like, what is the functionality?
We basically search something simply.
Yeah, I mean, yeah, that's a great answer, I would say. Okay, so why do you have the need for searching something?
To reduce the time, I mean, to
Uh-huh.
save time.
And if you don't have the search capability, how would you go about doing that?
Brute force, normal, like going through all of them.
Yep, yeah, yeah. So thank you so much. That's the idea here. We live in a world where we have too much data, we have too much information, we have too much content, and we don't have the time or the expertise to search for things, just by going one thing at a time. If you were to open YouTube and maybe scroll through like millions of documents to find that one movie trailer or maybe that one video that you wanted to watch, I think you might just quit YouTube, right? Do something else, maybe read a book. So that's about it. It helps people find information which is usually actually, presented in unstructured data, I would say, like text, video. If it was structured, maybe it was like, table-based, you might find a way to, get to that. But because it's unstructured, it's even more tougher. Okay, what is semantic search? I know it's the title of my talk, but just curious to know if anybody understands what does semantic search mean? Yes, please go ahead. The gentleman in maroon, yeah.
I think by semantic search you mean like having a particular kind of semantic or syntax by which we can search, for example, SQL query language. So that is a semantic search. But the other kind of search we can see is like fuzzy search, where we are like typing anything and it tries to match with the what kind of thing the user is trying to search, like with some kind of fuzzy index or fuzzy search matrix maybe. So probably that's.
Yeah, those are types of searches, but that is not semantic search. Anybody else would like to take a go at it? The person in white behind.
Extracting meaning from the sentence and looking for relevant answer which match the meaning or have some relation.
Absolutely correct. So the word semantic, it is kind of, related to the philosophy of meaning. So in natural language processing, when we say semantic, we try to sort of indicate that two things are semantically similar. That means that their meaning is similar, irrespective of whether their characters or the words used in those sentences are similar, are exactly same or not. When we say things are syntactically similar, I think that's what you were trying to answer, which is that we go for keywords, like matching keywords, matching characters. It could be fuzzy as well. Oops. There goes your answer. So it's not just about understanding the meaning, but why semantic search is important, and it is kind of, now become a norm with a lot of search engines and like people are kind of moving towards more semantic search than just keyword-based searches, that by semantic search, you can understand the intent behind why a user asked that question and not just sort of match some documents. And by doing that, the overall experience of any user who's trying to search for information automatically becomes better. Next question. Do you think Google uses semantic search? And please do not open your phones and search for anything. Just think about it. Has anybody sort of, yes, sir, in check shoot at the back? Yeah.
It uses semantic search in NLP processing.
No, but then how do you sort of prove that? Like, is there any observation that you have kind of noticed?
It is used in SEO, search engine optimization, NLP processing, right?
No, I think you are sort of going towards maybe the more, the SEO part of the things. It's actually not related to that. What I'm trying to ask is a simple question, which is, have you ever observed, like for example, if we've been using Google all our lives, right? Like our generation, or like, I don't know if how many of you are from my generation, but the point is that we've been using Google all our lives, but if you might have noticed, Google keeps on changing their search algorithm, right, from time to time.
Definitely,
Have you noticed any difference there?
Google keeps on bringing updates. With those updates, it has come to an semantic search updates has come through for Google algorithms.
But any example that you can give which proves that?
Examples would be in the results of search, what listings we are getting, those has changed with over time, how the processing is done for Google algorithm.
Okay, I'm going to take another answer from this side. Thank you for your answer. Yes, sir, you, in the front. Yeah.
So Google uses semantic search, like when you search for a, when you search for medicine, like that, it structures data differently. When you search for education part, like stuff like that, books and all, it structures data differently. So
That is not exactly semantic search.
that
That's kind of like maybe personalization or topical search.
why? But it is structured, so we can call it semantic. So
No, that's a
semantic
different.
means
That's
structured.
that's a different concept. What you're saying is correct, but it's not exactly what I'm trying to convey through semantic search. Anybody else? You at the back? Yeah.
Yeah, one thing I noticed, like Google keeps the context of our conversation or search with Google. So for example, I search process and then I search kill. So it will suggest me that I'm going to have or trying to search how to kill a process. So it remembers the context of the conversation or my search on Google.
Okay. Again, that's a great observation, but that's not semantic search. Because we have a shortage of time, and that's why I cannot take more answers. But the answer is yes. Google does use semantic search, and I'm gonna show you how. Oops. So I searched this in the morning today because I just didn't want to go to a wrong venue. If you think about it, this side, right? So this is an example of semantic search because my question is, where is Tal Kutir? My first response itself, even before I see any of the links, is the address of this place, right? This is exactly what I wanted to ask. Here, if there was no semantic search, so basically if I'm just typing some keywords, the responses are different. If you see, the ranking is also different, right? So this is keyword search. If Google was not, maybe like before they rolled out this update, and I think this was in probably 2018 or maybe slightly earlier, I would say the result of this query would have been something like that. So that means that this is not, if that query is leading to these results, that means it's a keyword-based search. But because I'm asking a question, I'm getting a direct response to it, that means it's a semantic search. Another example, I think everybody is a fan of Saurav Ganguly here. I just guessed that. So I asked, who is Saurav Ganguly, right? I get the proper answer here. Google understood what I'm trying to ask. I'm asking who that person is. I just type the keywords here. I get some, responses related to Saurav Ganguly. It's related. These are relevant documents. But this is again keywords, right? So because I did not express my intent of why I want results related to this entity or this person, it's just showing me some news articles. But because here my intent is clear, which is I want to know who this person is, the answer, the response is also relevant to that. I'm going to move forward now. Now that we've established that, this is semantic search and this is search in general, let's try to understand what is the underlying problem that we're trying to solve when we're building search engines. It's the class of AI problem, it's called information retrieval. I would say broadly, there are two types of information retrieval. So search is a type of pull-based information retrieval, and recommendations are a type of push-based information retrieval. And, okay, so I think you might have noticed that my abstract for this talk was very short because there is so much that I can package in this topic that I can't, I think it'll take a whole day or maybe more than that. So I'm going to keep things, at a high level and not get into like very specific details. But the idea here, like the information retrieval problem is that you have a list of documents, or you have some content, or you have some data, right? And what you want to build is a search capability. So you'll have certain queries, and the information need means that there's a need to sort of extract information, or rather pull information. And then, so that's the query. Your documents are there. You need to build a function which is able to retrieve the relevant documents with respect to the query and show you some ranked results. Why? Because nobody likes, if you ask about, say, Tal Kutir, and I'm getting that as a third link, nobody's gonna appreciate that. So, okay, now this is the problem. This is like the classical AI problem, which is information retrieval, which is behind search engines. But none of the AI systems in the industry are, just code. They are code plus data. Data is equally important. So let's try to understand what kind of data setting is required for building ad hoc information retrieval systems like search engines. So you would need a corpus of search queries. You'd need a corpus of candidate documents, or you can call it like a knowledge base or something else. And then there's a ground truth. What ground truth means is that for every document, like for every query, you will have a list of documents which are relevant to that query. And also you might have like negative documents. I think you can figure it out. Like for example, if you have 10 queries and you have 100 documents and each query is paired with 10 documents, that means the rest 90 of them are actually irrelevant to that query. So this is the data setting for the information retrieval problem. Now let's talk about the solution architecture. Have you guys ever wondered how does search work, either in Google or like anywhere? Have you been curious, how does it actually work? Has anybody actually explored how that works? I think people are talking about indexing and nice. All right. So this is a very generic architecture. And we'll come to why this is generic like later in this session. So you have offline steps. What I mean by offline is that you need to do it once, okay? You need to store the data in some kind of DB. You need to represent that data, that is your set of documents or your knowledge base or whatever you want to call it, whether it's content or whether it's text base. You need to represent that. By representation, I mean like machine learning systems don't consume text data directly. You need to have a way to featureize that data into some kind of vectors. So that talks about that. The second point is document indexing. I think that gentleman talked about that. That's just a way of tagging the data or storing it in a data structure that makes it easier for us to pull that information. When a query comes, we're able to pull the relevant information easily. There are online steps. Now, this happens every time. Once you've done that, this will happen every time, or in machine learning world, we call it as, this happens at the inference time. So you'll have, like for example, now I've built my search engine and my data is indexed. Now when I type a query, my query needs to be represented similar to my document vectors. There has to be the same representation of my document vectors or my candidate or my knowledge base vectors, and the same way my query has to be represented. The other thing is that we need to retrieve the candidates. Like for example, if I have 1 million documents and I have a query, I can't pull all of them and then rank them. I think it would be like really time consuming and quite inefficient to do that. So I need a step in between where I'm just retrieving the most relevant candidates. And then there's a ranking step involved, which is making sure that it's actually more relevant when you talk about like contextual or personalized search. But nevertheless, there's a ranking step which takes care of the fact that whatever you see is ranked in a proper way, and you see the most relevant document or the most relevant information ranked as the first item in your list. Okay, so text representation. Have people here heard about embeddings, word-to-vec, TF-IDF, one-hot encoding? Okay, again, I just wanted to understand like if people actually are aware of this, or should I probably take a step back and then explain? So we have to represent text as vectors. If this was numerical data, we'll create features, and those features would be represented as vectors. But now because we have text, we have to represent this text into some information which will convert them into numbers. you can do something very simple, which is one-hot representation. What it means is that I have a sentence and I have like, I would say like, I have a list of documents, and my features are basically one-hot encoded vectors. What it means is that whether a term or like a word is present in that document or not, that is what it stores out of the entire vocabulary. But that's not a great representation of maybe semantic search queries, because when we say semantic search, we're automatically kind of targeting sentence-based queries and not keyword-based queries. You can also have character n-grams. So instead of like just maybe, you want to figure out if the search query is kind of matching with some parts of, the words in the document. So that's like, like sub-segments of words. These are sparse representations and may not be as accurate, but then there are dense representations which actually capture the semantic meaning of these documents and the query vector, right? And those are really, I would say, of use here in case of semantic search. So you can represent your terms. By terms, I mean like tokens in the query. Like if you say have 5 sentences, what is there for lunch today, and you learn the representation of each of these words, or you can learn a dense representation of the sentence vector itself. My time is already up, so I'm going to rush through some of the slides now. How to choose any representation? Well, all right. So choosing the right kind of embeddings or featureization technique depends on the size of your data, the properties of your data, whether you have short text or long text, whether you have long documents or shorter documents, and also the domain in which you're operating. Then, deep neural networks, as we say, they capture like a lot of meaning and essence of what the document actually conveys. They can be learned in situ. That means that you can use your custom domain-specific data to learn these and train embeddings from scratch, or you can use some already trained models like pre-trained embeddings and use them directly for featureization. What you need to keep in mind is it would always be better if you use certain pre-trained embeddings which are actually suitable for the task at hand. For example, if I have to, if my task kind of translates into like a text-based similarity search, maybe using a model like a universal sentence encoder might, or maybe a sentence transformer might be better than using maybe say a Bhatt-based model, because these models have been trained on the sentence similarity task. Again, it's not necessary that you always use embeddings or dense representations, because sometimes maybe a combination of both would be good. And I can give you an example of that. Like for the same question, like about Saurav Ganguly, somebody might just type Saurav, and somebody might write the whole sentence, who is Saurav Ganguly? So you need to cater to all kinds of users, and hence a combination of these two techniques might be more effective. Indexing, as I mentioned earlier, it's just a way of sort of storing your data in a more optimized way and tagging it such that when you're using, when you're actually retrieving candidates relevant to your query, they're easily available. Okay, candidate retrieval, this is kind of a interesting topic here. The core idea here is that you have a query vector and you have a document vector. You need a technique to sort of derive some kind of relevance between your document vectors and your query vectors. And then once you have some kind of estimated measure of relevance, you want to rank your documents according to that relevance score. But do you think like whatever we discussed, this is enough for building a semantic-based search engine? Actually, no. A lot of it depends on what setting you're operating in, how much data do you have, and by data, I mean like unlabeled and labeled. For example, if you have no label data available, it's okay for you to go with a completely unsupervised approach, and what you can use is you can use some kind of a cosine similarity metric to rank your documents, right? Whatever you retrieve in the candidate retrieval stage, you can just re-rank them basis the similarity score, the cosine similarity score between the query and the document. This is completely unsupervised approach. There is no direct supervision that you actually have at hand. If you have some small amount of labeled data, task-specific data, and you have a large amount of unlabeled data. Maybe you're not a big company and you're like a startup and you don't have the budget to actually annotate a lot of data. This might happen in that case. What you can actually do is train a retrieval model, which will actually, with few parameters, which in turn is kind of learning representations from pre-trained embeddings or some other large language model. If you are a big company and you have a lot of labeled data, then you can always go with a fully supervised approach and train a retrieval model that directly optimizes for the target task, which is your retrieval. So this is like your best case, but this, I would say this rarely happens until you're like one of the FANG companies. All right, so ranking, we were talking about ranking and somebody mentioned that, the results would depend on like a lot of things. That's actually true. Here, if you see, so if I had entered the same query when I was in Bangalore, I would have gotten different results. But because I entered this query on Google while I was in Kolkata, my results changed because my location changed. And this is how ranking, the reason for this is your ranking component of the search engine. Okay, ranking approaches, again, if you don't have any label data available, as I said, you can just use a cosine similarity metric to rank that, and that's your unsupervised approach. If you have label data, and not just label data in terms of relevance, but also maybe in terms of like, what should be the ranking? Like, for example, for a query, I have 10 matching documents, and what should be the rank of each of these documents? Then you're good to go. You can go with a supervised learning to rank. I did cover everything. So yeah, learning to rank method. These are costly algorithms, but again, depends on your appetite and your availability of data. All right, this is something which we hear a lot when we're like in the applied ML industry. You can't improve what you can't measure. So whenever we're working with ML models or any kind of systems, we have to constantly measure things so that we know what's going well and what's not going well and how can we improve. So I'm going to briefly talk about like some of the metrics for information retrieval. There's mean average precision. I hope people know about like precision and recall. It's just like, sort of targeting towards like if you are predicting something, how many of them are actually correct, like as compared to the ground truth, right? MRR metric, which is the mean reciprocal rank, it actually just focuses on your first, the ranking of your first relevant document. It mainly focuses on that. The NDCG, or normalized discounted cumulative gain, is also kind of similar to MAP, and the whole idea here is that you would want most relevant documents to show up first, then medium relevant documents, and then the least relevant documents. So it's kind of overall optimizing for your entire list of things and not just the first ranked element. These are offline evaluations, and this doesn't depend on what we get from the user, right? The online evaluations are basically when we take the feedback of the user in mind. And I think somebody was talking that, Google actually takes into care, like if I wrote kill versus process kill, and then, it'll predict my query. So this happens because of this. So it tracks the click-through rate. Like if I'm showing you certain results, what's the probability, or rather, like how many times do you actually click on those results? View rate is basically not just clicking, but actually viewing and reading the documents. This can come into handy, not just Google, but other kind of search, maybe just document search kind of search engines as well. And then A/B testing is required to figure out, like, if you have two algorithms and you have an app, at the same time, like, you're confused, like, whether to roll out model 1 or model 2, you can have an A/B testing setting and have, like, one model exposed to, say, a section of your users, and another model or another system exposed to another section of your users, and you can monitor their results. It's not completely accurate, but it will give you a good idea of which one to go forward with if you have randomized your population well. All right, so we were talking about feedback loops, and this is very important in search applications. I think as ML practitioners, we might feel that our job ended when we calculated MRR or MAP or NDCG, but our work actually starts here. So when the users start using your application, you have to closely monitor who is seeing your result, what are they seeing, which are the results which are getting a lot of clicks or not, and on the basis of that, is user taking an action? And on the basis of that, is there a way that you can improve your system? Okay, so I had mentioned that I'm going to talk about why is search so difficult. These are a quick, set of reasons I would say, and this is personally that I have sort of encountered as well. I've worked on building semantic search engine in Jupyter as well. So data drift, right? We start with some data, and we build systems with that data in hand. But when users actually start using our applications, and then like Jupyter is kind of in growth phase, right? So we went from like 0 to 1 lakh to now 1.5 million customers very quickly. Now, the kind of assumptions we use to build those applications, it's not necessary that those assumptions will hold. And same will happen for your data as well. So there will be data drift. What I mean by data drift is that the data you started with might not be applicable later on, and you'll have to constantly keep updating your systems to account for that. Another problem is spelling errors. I think users have fat fingers. They'll always make spelling errors, irrespective of how much Google Keyboard actually provides the capability and predicts like spellings for people. People still make a lot of spelling errors. Personally, I have observed that a lot while working on semantic search engines at Jupyter. Domain adaptation. So I work in the fintech domain currently. I use models which have been trained for the general domain data. At times, there's a lot of issues because, for example, balance in finance word means something else, while balance in general domain means something completely different. So then, if your model is not understanding that, you need to understand that it needs to be fine-tuned with some domain-specific data for it to learn the accurate representations. Lack of data, whether it's unlabeled or labeled, this will always become like a bottleneck when you're building like accurate search engines. Zero results or out of scopes. So you have to keep this in mind that if you have, say, 100 documents and you've indexed them and that you've built a search on top of them, there'll be some user who's going to ask a query which is not going to match with any of them. Or worse is when the user asks a query and an irrelevant document is shown to them. So you have to keep in mind that there are going to be these kind of negative scenarios or corner cases, and you have to build and accommodate them. These are some ways to sort of target these problems, which I listed in the previous slide. For data drift, you need to monitor what's the data drift and use active learning feedback loops. Basically, use real data and then keep on updating your systems. Eventually, the data drift will kind of converge. Rather than your data, like one distribution is going this way and the other distribution is going this way, they'll start converging. Autocomplete feature, I think you must have used this while using Google. So when you start typing something, it kind of predicts also. A lot of applications do that. They kind of predict what you want to type. And I think this can help just prevent spelling errors. If you don't have the capability, because this is also a very tech-heavy, AI-heavy application, if you don't have that capability, you can build some custom spell checkers as well. But then if you have domain-specific data, that is still going to be a really difficult problem to solve. Transfer learning, I think I talked about this. If you have domain, like you're working in a very specific domain, like e-commerce or biomedical or maybe like finance, and you don't have domain-specific data, you use whatever little data you have, the domain-specific data that you have, and you have to fine-tune your large pre-trained language models. And over the period of time, as your data grows, your fine-tuned models will also start representing your text in a much better way. You need to analyze your search query data, and this is of paramount importance. I think the best way you can maintain the quality of any ML system is keep analyzing, keep identifying where it is sort of breaking and where it is causing errors, and keep fixing that. So for example, if I probably built a search engine keeping in mind that my target audience is, they're good with English. They understand English and they want to prefer English. But that's not the use case. That's the data drift that I observed. That most of the people want to speak in their native languages, or maybe Hindi, or maybe maybe Kannada. I don't know. But can I just start jumping on building like a regional or a multilingual model for my system? I don't think so. I need to first understand what's the gravity of the problem. So we always use, we call it as Pareto principle. There's an 80-20 principle which is always used in the industry. If you feel like this problem is actually being experienced by, say, 80% of your users, or maybe 70% of your users. You can set the cutoff there. Then you pick up and solve it. If it is being, just experienced by a small section of the users, you park it. I'm not saying you don't solve it. You park it because there are going to be other problems that will take more priority than that. Data augmentation and synthetic data creation, I think this comes in handy when you have very less data. The last one is handling zero results and out of scopes queries gracefully. How you do that is just try to understand like the distribution of your similarity scores and try to figure out what is the cutoff. Like say for example, if the cutoff, I set the cutoff as 0.6, right? And my similarity score ranges from 0 to 1. So if there's a query and the best matching document, the similarity score for them is like say 0.5, I'm not going to show that. What I'm going to show to the user is that there is no matching document. That would be a graceful exit. Rather than showing something irrelevant, completely off topic, that might just, kind of discourage your user to use your application. Okay, these are again slightly more, I would say, behavioral kind of aspects that you can measure and improve. Just try to improve the content if people aren't clicking on the search results. Maybe you're showing the right things, but people aren't really clicking on that. Something is wrong with the kind of information that you're showing on top. If a content is prominently, it's getting a lot of clicks, then you need to make sure that it gets discovered by more and more users. And yeah, it's not always the fault of the search engine or the application. Because these kind of applications are embedded in your apps, in mobile apps, it could also be that the user is not able to find the right information, hence coming to search for things. So just also take a step back and figure out if the UI or the UX design is appropriate or not. Okay, so beyond semantic search, I think a couple of people talked about here. So you can have personalized search. I think I gave an example there that, depending on my location, my search results would change. You can have traditional keyword searches any way, like, it's kind of operable at a lot of places, like WhatsApp does that. Recommendations, again, as I said, it's push-based retrievals. The fundamental, core problem is same. It's just that instead of pulling certain documents and showing the result, what you're doing is you're kind of doing that again, query and document similarity matching. At times, you're not even doing a query matching because recommendation engines also work on your historical data, and they just want to rank some content or some results for you so that you get to see the most relevant things up front, like YouTube uses that. And domain-aware matching, as I said, you can have ontologies. I'm not going to get into like the whole complexity of that, but it's just a way of sort of mapping your domain knowledge into some kind of a graph, which can then be used by these applications to give you more accurate results. All right, that's about it. I'm so sorry it took a lot of time. Sorry, Ankita. But any questions? Yes, sir, please go ahead.
Hello. Ma'am, you mentioned about domain adaptation. So can you please give some brief explanation on domain adaptation and its types?
Okay, so what I mean by domain adaptation is that, see, you can solve that problem in two ways. A is you have a lot of data, whether it's unlabeled or not, and this comes into picture when you want to vectorize your text data, right? You need to, for example, if I have a lot of, I'm operating in the finance domain, right? If I'm using a model which has been trained in general domain, there would be issues. There would be things which it wouldn't understand. For example, like in the finance domain, there's like balance. There is like, we use a concept called pots, which is for saving your data into like, more, these are more like piggy banks and all. So, but these words also have a meaning in general domain in which these pre-trained models have been trained for, right? So you can't let your model represent your text in an incorrect way. While I, like, in the domain, it means something else, but because I'm using a pre-trained model which has been used in general domain, its meaning is going to be represented in a completely different way. And that can mess up my search results or how I'm matching my documents. Hence, what is required is that the model that I'm using for vectorizing my queries and documents that need to be from the same domain. How do I do that? Either I use a pre-trained model and I use some task-specific model, some unlabeled data from this domain, right? I have some documents which talk about like account balances. I have some search queries from actual users. And I use that data to actually fine-tune the pre-trained model. By fine-tuning, what I mean is I freeze the initial layers of the model. So I'm kind of preserving the structure of language that it is learning, but I'm kind of fine-tuning it on a task. The last layers, I'm kind of fine-tuning it on a task, and that takes care of the domain adaptation. So it also learns the feature from that domain. Or if you have a lot of data, you can train it from scratch. So you can train a language model completely from scratch if you have a lot of training data.
Thank you, ma'am.
You're welcome. Any other questions? Yes, please.
Ma'am, you said that the searching depends on the query and the document vectors. So what if there is a mismatch between the query vector and the document vector, but the relevant document is available, but due to the mismatch, the results are not shown?
Can you sort of maybe rephrase your question? So you're trying to say that there is a relevant document present,
Yeah.
but it is not shown.
Yeah, due to the mismatch between the query and the document vectors.
So that's the reason we build search, right? We need to have that matching function, or you call it like the relevance function, which will take care of that. If it is not being shown, then we need to fix the algorithm. Then we need to figure out. So that's how you estimate. So all of these are kind of probabilistic in nature, and you need to estimate what should be the parameters of these functions, right? This is how you learn it. So if you have the ground truth, you're going to train it for that task. So if you're using some kind of supervised retrieval model, that is the task it'll be sort of trained on. That if there's a relevant document available, that should be the correct result. If it is, your model doesn't learn that, you need to keep on training that. That's for the supervised thing. For the unsupervised thing, I think you need to figure out like, maybe your the featureization technique or the embedding is not really working, and you need to fix that. Most likely that's the cause.
Thank you, ma'am.
No problem, thank you. Yes, please, yeah.
Guys, just excuse me for a moment. Shweta, please. What
Sorry.
we'll do is we'll take the questions later on. We're actually running a bit of short of time. So if you have any questions, don't worry. We'll have a high tea session, and after the event, she'll be around. You can ask all your questions there.